Hi everyone, I'm doing a review of the chain rule and we'll go through some examples shortly. So the functions on the right and the associated derivatives we will be using in our examples. So I will take that as assumed knowledge. So the chain rule applies to composite functions, which look like what we have here. So f of g of x. And we take the derivative of this kind of composite function by first taking the derivative of f with respect to g of x, and then multiplying that by the derivative of g with respect to x. And writing it this way, we refer to as function notation. And often we prefer to use Leibniz notation, which makes it a little bit more explicit what we're actually doing. So equivalently, if we write, if we let u equal to g of x, then taking the derivative of both sides, we get du dx is equal to g prime of x. And so this du dx we know, or we refer to as Leibniz notation. And we express the chain rule like this. So dy dx is equal to dy du multiplied by du dx. Right, so we first take the derivative of the function, the original function, with respect to the innermost function, if we want to think of it like that, and then the derivative of that function with respect to x. So we have this, and then an equivalent way of expressing it. Okay, so let's look at our first example. We can see it is, or it has the form of a power function, only instead of x to the n, we have a function of x to the power of n. So let's use our substitution. Let's write that y is equal to u to the power of n, right? Where u is the inside function, or g of x. And u we will define as ax plus b. So taking the derivative of y with respect to u, we can just apply our normal power function rule, which is nu to the power of n minus 1. And the derivative of u with respect to x is just a, since a and b are constants. So just rewriting our chain rule in Leibniz notation. Okay, we've already taken our derivatives, so we can just copy down dy du, which is n times u to the power of n minus 1, multiply that by du dx, which is a. Okay, and because our question only, or our original function was a function of x, we can't express our final result using a u, right? We need to replace it with, or we need to write it as a function of x. So ax plus b to the power of n minus 1 multiplied by a. I'm just going to put the a in front here. So that's our result. Now, to save time, you don't always have to write down all of these y, u, dy, du, du, dx. As you gain practice, you will be able to look at the original function and immediately say, I'm first going to treat the bracket as if it were x. So power rule, right? N to the power n multiplied by the thing inside the bracket to the power of n minus 1. And then chain rule, so derivative of the inside, that's just a. Okay, and then whatever was inside the bracket, we'll just write down here. And then as you can see, we've obtained the same result as we did on the left, but with far less writing and far more efficiently. Okay, next example. Again, it looks like a power rule. Okay, I'll do the substitutions again. So y is equal to u to the power of -3. U is equal to 1 minus x squared. The derivative of y with respect to u is equal to -3 multiplied by u to the power of -3 minus 1, which is -4. And then the derivative of u with respect to x, derivative of a constant is 0. And then over here, the negative sign stays, and then we apply the power rule. So 2 times x to the power of 2 minus 1, which is 1. Therefore, the derivative of y with respect to x, okay, dy du dx, that is -3. Now replacing u with the expression in terms of x, right? Because our original expression was in terms of x. 1 minus x squared to the power of -4 times du dx, which is -2x. And we can rewrite this a little bit more neatly by simplifying a little bit. So negative times negative is positive. Okay, so on the top we have 6x. We have a negative index, so the 1 minus x squared to the power of 4 goes in the denominator. And that's our result. Okay, so once again, we could have done all this in a more efficient manner without writing all of this down by looking at our original function y and straight away applying the power rule. So taking the exponent down, -3, okay, keeping that bracket there, -3 minus 1, -4. By the chain rule, we have to take the derivative of what's inside the bracket. So then multiply this by -2x. Okay, and then whatever was in the bracket originally stays there. Okay, and then simplifying, you'll see we get exactly the same result as expected. Okay. Next example is a little bit more algebra, but the same principles apply. So let's go ahead and use our normal u variable, right? So y just becomes u squared. Okay, we'll define u as the inside function, right? So x plus square root of x squared plus 1. And I'm going to suggestively write this as x plus 1/2. Sorry, x plus x squared plus 1 to the power of 1/2, right? Because we need to apply the power rule to this, of course. Okay, so derivative of y with respect to u, that's just, you bring the exponent down, okay, and then 2 minus 1 is 1, so 2 times u. Du dx, okay, derivative of x is 1. And then over here, okay, this is a power function, so bring the exponent down, which is 1/2, okay, and then whatever was in the bracket stays in the bracket, right? This is like another application of the chain rule. 1/2 minus 1 is -1/2, multiplied by the derivative of the inside, that's the chain rule part, 2x. Okay, so let's write down our results. dy dx is dy du times du dx. Okay, so we have 2u, and let's just write down what u was. X plus x squared plus 1, all square rooted, multiplied by this messy expression, which I will rewrite as 1 plus. So we notice that we have a 2 in the numerator and in the denominator. So they should cancel out, right? And then here we have a negative index, which we can put in the denominator. So the x stays on top. Okay, so this does not quite look like our desired results up here at the top yet, but we can rewrite it to make it look like that. So let's put the expression inside the brackets on the right under common denominators. So keeping this left-hand side unchanged. Okay, we recognize that 1 is equal to square root of x squared plus 1 over square root of x squared plus 1. Okay, so this will allow us to combine the numerators. Okay, and then we see that we end up with x plus square root of x squared plus 1 over square root of x squared plus 1. And now we're basically there, because you notice that this numerator is the same as the expression inside the bracket on the left. So we can rewrite this as 2 times x plus square root of x squared plus 1 squared all over square root of x squared plus 1. And that was our desired result.